Hello, I am Ahmad, and in this video, I'm going to talk about strain energy and total potential energy in a beam, which is under bending moment. So we are not covering axial force, torsion, or shear force, just about the bending moment, internal energy and external work, and the total potential energy. Assume that we have a beam under a given load. And due to the load and the length of the beam will be under bending, so it will bend. Now we are going to determine what is the external and internal work in this beam. So in other examples, in the stability course, we calculated for the rigid elements. When the element is rigid, then there is no internal energy. But when it is deformable, for example, under bending and the material can bend, then we need to calculate what is the loss of energy and what is the gain energy or stored energy. So first, let's go through the loss of energy. For this, we select a tiny length of the element, assume that horizontal direction or longitudinal direction of the element is called x. This is dx, and after deformation, its length will be again dx. And the rotational angle, let's assume, is theta. So what is the shortening length of the element? du. Du is the shortening of the element. So du can be written as dx minus dx cosinus theta. If I factor dx, it will be 1 minus cosinus theta. And we know that cosinus theta is square root of 1 minus sinus 2 theta. So then I can rewrite this du will be dx times 1 minus square root of 1 minus sinus 2 theta. As far as theta in the deformation is very close to 0, from Taylor series around 0, which is called Maclaurin series. So I have another video to explain how these equations can be calculated. So sinus theta, when theta approaches to 0, can be written as theta. Then du will be dx times 1 minus square root 1 minus theta power by. Theta is the rotational angle of a beam. So here is a beam, and here is the formed shaped. As a result, this tangent is called theta. If the longitudinal direction is x and the deflection is called v, then from the basics of mechanics we know that theta is always v prime. As a result, I can rewrite du as a function of the v prime. So du will be dx times 1 minus square root of 1 minus v prime. power by 2. Again, from the Maclaurin series, I can write down that square root of 1 minus v prime power by 2 is 1 minus 1 over 2 v prime power by 2. So it will be 1 minus 1 minus 1 over 2 v prime power by 2. Then it will be 1 over 2 y prime power by 2 dx. Now, if we have a beam starting from 0 to L, and you want to calculate what is the loss of energy due to the loading, so dV, which V represents the loss of energy, will be minus P times du. And we calculated du earlier, then dV will be minus P times 1 over 2 V prime power by 2 dx. As a result, V, or the loss of energy due to deformation, will be minus 1 over 2p integration from 0 to L v prime power by 2 dx. This is the energy that will be lost in a beam, considering only bending and elongation. Now, let's go to the gain energy, or the potential energy that is stored due to the bending. Suppose this is a tiny length of the beam, and this is its neutral axis. And assume that the beam follows the Euler-Bernoulli hypothesis, which means that the height of the element is far smaller than the length, or h over L is very small. As a result, the plane remains plane and there is no distortion of the cross section. So after applying the force, which in this case will be bending moment, we will have the deformation of this element. Very exaggerated. We know that the neutral axis will remain the same, so there is no elongation in that. S-train is 0. And so after bending, the system would have a kind of curvature. And the curvature has its own angle. Let's call it d theta. We know that the radius of this curve will be rho, or we name it as rho. From the basic mathematics, we know that the dx is rho d theta. Consider that rho represents the curvature radius from the neutral axis of the element, or of the cross section. Now, consider a section above the neutral axis, which is in the distance of y from neutral axis. And I call this A, B. So initially, before applying the bending moment, the length of AB was dx. But after bending, it is now if the bending moment is positive and AB is above the neutral axis, it is shorter than the original length. So now we are going to calculate what is the elongation length of this AB. So AB will be rho of AB times d theta. Rho of AB is rho minus y. So it will be rho minus y d theta. So AB after deformation is rho minus y d theta. AB before deformation or before applying the load was dx. Now, by the use of AB after elongation or shortening compared to initial length of the element, we can calculate what is the deformation. So delta AB will be AB1 minus AB0, which is rho minus y d theta minus dx. And we know that dx is rho d theta from here. So d theta can be written as dx divided by rho. Then delta AB will be rho minus y dx divided by rho minus dx. So delta AB will be rho dx divided by rho minus y dx divided by rho minus dx. These two will vanish, and as a result, I can write down that delta AB is minus 1 over rho y dx. We know that y over rho is called curvature and is sketched by kappa. So delta AB will be minus kappa y dx. So we can derive to d of delta is minus kappa y dx. This is the tiny elongation of the element, and this is a function of y representing at what elevation from the neutral axis we want to calculate the elongation. Now if we look at the section at the elevation y from the neutral axis, so assume that this is neutral axis of the cross section. It doesn't matter what kind of shape do we have, and assume that after applying the bending moment, this part is under stress. And we can assume that the area of this element is dA at the distance of y. So then the force that is applied to this part, as far as it's a very tiny, we can write it down as dF. So dF will be sigma dA, stress times the area. And if we are in an elastic phase, so sigma is E times epsilon. So dF will be E times epsilon dA. Now, differential of the gain or stored energy is differential of the force times the displacement divided by 2. So this is half of the work that is done. So in the beginning, force is 0, and at the end, force is dF. As a result, it's an average value of dF times d delta. Now I can substitute dF by E epsilon dA. and times d delta divided by 2, and epsilon is d delta divided by dx. So it will be e times d delta divided by dx. I put 1 over 2 as a factor, dA times d delta. From equation number 1, I can substitute these values to dw. So dw will be 1 over 2 e times d delta divided by dx is minus kappa y times dA times d delta, which is minus kappa y dx. So it will be 1 over 2 e kappa power by 2 y to dA dx. Now for calculating the total stored energy inside the beam due to bending, we can integrate from 0 to L 1 over 2 e kappa 2 y to dA dx. So dA is the differential of the cross-section area, which is independent from the length of the x. It can be in any section, and if it's a constant section, then it is not going to change based on the length of the element. In any length, in any cut, it will be the same. And y2 times dA, integration of that, is representing the second moment of inertia. As a result, I can write it down as integration 1 over 2 e kappa integration y2 dA dx. This is on the domain of A, and this is from 0 to L due to dx. So if I call this as I, so it will be from 0 to L 1 over 2 e kappa I dx. And from here we can write the total potential energy of a beam under the bending moment. So W is 1 over 2 integration ei kappa 2 dx. We can keep I inside, and if there is a constant section, we can take it out from the integration. If it is not, I will represent the moment of inertia in every section of the beam. So from 0 to L, minus 1 over 2 p integration v prime power by 2 dx. The next, we can also calculate what kappa is. Kappa is mathematically minus second derivative of v divided by 1 square root of 1 minus v prime power by 2. So if I multiply numerator and denominator with 1 plus y prime power by 2 square root, so it will be minus second derivative of v times 1 plus v prime power by 2 divided by 1 minus v prime power by 4. And we know that the rotation of a beam at the distance of x is very close to 0. So as a result, v prime power by 4 is very, very close to 0. And this can be rewritten as second derivative of v times 1 plus v prime power by 2. Also from the Maclaurin series expansion, we know that 1 plus v prime power by 2 can be, if v prime approaches to 0, 1 plus 1 over 2 v prime power by 2. So kappa will be second derivative of v times 1 plus 1 over 2 v prime power by 2. And now if I substitute kappa with the equation, this is very useful when, for example, we want to calculate the post-buckling questions. So pi will be 1 over 2 integration vi second derivative of v power by 2 times 1 plus 1 over 2 v prime power by 2 power by 2 dx from 0 to L minus p over 2 integration of v prime power by 2 dx. Yes, we went through the calculation of total potential energy of a beam under bending moment, and if we compare what we did in the rigid element with the method that we used here for a beam, we can distinguish how they are relevant, and they are very simple in any case. Thank you for watching, and see you in the next video. Bye.